Hello everyone, Tyler here with part 2 of our 3-part special episode on hazardous electromagnetic events like EMPs and coronal mass ejections. In part 1, we discussed how electromagnetic energy is able to harm physical objects like electronic devices. And in part 3, we'll discuss how this is able to harm our way of life. But today, we're going to discuss the events that can actually cause harmful electromagnetic saturation. Before we get started, I want to say that this is a grave topic and this may be a lengthy video, so for those of you who just want the summarized version, that will occur at this time mark. Thank you to everybody for watching. Let's jump into it. Before we get started, I just want to highlight once again the fact that I'm just a regular guy sharing my understanding of complex topics. In this case, I want to point out that I've been incorrectly referring to solar flares and coronal mass ejections as the same thing. Though they often happen at the same time, solar flares are in fact just the release of speed of light energy, like visible light and X-rays, from a single point on the Sun, whereas coronal mass ejections are eruptions of plasma, physical mass like ionized particles and other things, as well as electromagnetic energy from the surface of the Sun. But these travel slower than the speed of light outward in a wave pattern from the Sun. Solar flares take about 8 minutes to travel to the orbit of Earth, whereas coronal mass ejections can take up to 3 days, although in one case they've been recorded in about 17 hours. In both cases, it's important to remember that the relative positions of the Earth and Sun are important. For the sake of our discussion, we're going to focus on coronal mass ejections, because solar flares are classified as specific wavelengths of energy, whereas coronal mass ejections include charged particles like ionized hydrogen. And these affect our magnetosphere in specific ways that we're about to discuss. To understand the effect that EMPs and CMEs, coronal mass ejections, can have on the Earth, we need to actually step far, far back and take a look at the basic nature of our solar system. The conditions of our entire solar system are dictated by our Sun. The Sun is a nuclear blowtorch, blasting powerful radiation outwards in all directions in the form of electromagnetic energy and charged particles, usually ionized hydrogen. This solar wind bombards everything in our solar system, blasting outwards to the edges of the teardrop-shaped glob that we call the heliosphere. At the edges of this heliosphere, this solar wind meets charged particles from the intergalactic medium and forms what we call the heliopause. Fascinatingly, the Voyager 1 and 2 spacecraft launched in the 1970s have just recently entered this region of space, giving us a lot of information about the boundary between our Sun's energy and energy coming from outside of our solar system. Back here at the distance of Earth's orbit, or at 1 astronomical unit, the intensity of this surge of energy is so strong that without some protection, water would boil off at sea level, and the Earth would quickly be left a black, barren rock. The magnetosphere is a super powerful magnetic field produced by the spinning molten iron core of our planet, which swirls and captures electromagnetic energy and charged particles. This forms a protective sheath, which intercepts and captures charged particles and hazardous rays, which would otherwise rain down onto our sheltered habitat beneath. This is fundamental for our safe living down here, so let's look at how it can go wrong. During a coronal mass ejection, the Sun's output of energy and charged particles increases exponentially. And when all of this interacts with the Earth's magnetosphere, it can cause much of the energy and particles trapped there to cascade down on the Earth, not unlike a river overflowing its banks. This can cause magnificent visual effects, which we call Aurora, and electromagnetic interference. This is always occurring to some degree somewhere on the Earth because of natural interactions between the solar wind and the magnetosphere. But during events like large coronal mass ejections, this can increase many times and cause very dangerous effects here at ground level. In the year 1859, the Sun released a series of coronal mass ejections which intersected with the Earth in its orbit, resulting in the first known documented cases of astronomers reporting solar flares. This event is actually referred to as the Carrington Event after one of those astronomers. This was a very powerful coronal mass ejection, which caused auroral displays across much of the affected hemisphere, exposing people and cultures which had never experienced this phenomenon and causing some level of panic. What's more notable is the effect that this event had on the most prevalent electronic device of the time, the telegraph. Telegraph operators reported that they received shocks just from touching the device, and that they were able to operate it without the usually necessary battery power source. There are also reports that some telegraph wires sheathing caught flame due to the heat produced in the wires by the inducted energy from the event. It is widely agreed upon that if this occurred today, it would cause severe and irreversible damage to our global infrastructure. This is compounded by the fact that in the year 2012, a coronal mass ejection of similar or greater intensity was released from the Sun, although fortunately, it passed through our orbit while we were elsewhere. This threat is further compounded by the fact that it could be triggered by groups like terrorist entities or rogue nation states like North Korea. At first, even the US military neglected to understand the EM pulse that was present at a nuclear detonation. Compared to the numbing and devastating blast effects of a nuclear detonation, the electromagnetic pulse seemed insignificant, especially in an age without as many prevalent electronic devices. As the Cold War progressed and nuclear technology developed, the electromagnetic threat was recognized. It was realized that no matter how large the yield of the weapon, the blast radius of a nuclear bomb could only get so big, but the electromagnetic pulse traveled far beyond this radius. What's more, it was discovered that the higher the altitude of the detonation, the farther the electromagnetic effects were scattered. With the development of the intercontinental ballistic missile, the world of nuclear warfare changed dramatically. Icbms operate much like a space shuttle. A multi-stage rocket system propels the payload into space, where it travels above the atmosphere until it is ready to release its payload or multiple payloads, where they will use rocket power to travel down to their designated targets. Especially when you compare them to Cold War airplanes, ICBMs are extremely difficult to defend against. This is due to the fact that they travel so fast and much of their travel time is done in the lower reaches of outer space. Current missile defense systems identify the threat while it's in space and intercept the payload as it approaches its target to prevent nuclear strikes on targets. Because of the speeds at which an ICBM can travel to and through space, it may not be possible to intercept them before they can detonate in the region of space necessary to cause the hazardous electromagnetic cascade that can cause such devastating effects here at ground level. Because of this window of opportunity, it is currently very possible that rogue states could cause a devastating electromagnetic event anywhere in the world, without interference from outside sources. Because of the unpredictable nature of these two threats, they are two of the major concerns for myself and many preppers that I am aware of. So to summarize today's video, we clarified the difference between solar flares and coronal mass ejections. We revisited the powerful and protective magnetosphere that surrounds our planet and looked at how it can be affected by coronal mass ejections and nuclear detonations to rain hazardous electromagnetic radiation down onto us, which can cause devastating effects to our electrical infrastructure. Thank you everybody for watching. I hope that you'll stay tuned with Let's Talk About Prepping for Part 3, where we'll discuss some of the real-world effects that these hazardous events can have on our own lives. Stay safe, everyone.